Okay, so this is going to be a continuation of problem 729. So 729 asks you to write a program that will find the maximum transfer shear in this problem where all these parameters are given as forces. So in the prior video we kind of went through and derived the governing equations, all right? We looked at the equations to get the geometric properties, the area moments, and the both the Q's and the I's, and then also we looked at how do we get the maximum shear. So we looked at considering the point load and then the distributed load and then superimposing those. All right. So basically, all I've done here is just set up a simple mathematica notebook, which is, I mean, basically a program in the sense that you have well-defined input and then it calculates values based on equations, okay? So, you can make it look nice and import little pictures in here, right? Here are the input variables as defined up here in the picture. D1, D2, A, L, H, B, T1, T2, P, W. The first thing we do is process that section, so all those are known variables now, they all black out. Then we compute the geometric properties, so here first we compute I. So we compute I for the web, and then I for the top flange, and here is the top flange shifted by parallel axis theorem. So here are the values of I. Then we do the same thing to compute Q, so here's Q of the web, and then here's Q of the top flange. Well, I should say that's of half the web. These are the values for Q after it computes those. Now we go back and do the shear diagram calculation. Sorry, compute the shear force. I didn't do the diagrams, but here are the forces. So we consider the two cases, right? We consider the point load and the distributed load. So for the point load, we get the reactions at A and B. The one denotes that it's for the point load case. Right. Here are those values. Then knowing those, we can get the shear forces at points A and B. We'll do the same thing for the distributed load case. Here are the equations for the reaction forces. These are the equations derived last time. Likewise, we can get the shear at the ends due to the distributed load. Then we're going to use superposition. We'll add those together, all right? So the shear stress at A is the sum of those two, and the shear force at A is the sum of those two, and the shear force at B is the sum of those two. Now, to compute the maximum stress, you need to find which is greater, A or B, and it's the max absolute value. So here we look at computing the maximum of the absolute value of the two. And it turns out you get the 315 over 2, okay? Well, I'm sorry, the 385 over 2. That's the max, right? It's this value, even though it's the negative. Then use that to compute VQ on IT, and this now gives me the maximum shear stress. And that's it. And so if I wanted to go back and change some of the parameters, so for example, what would happen if D2 were to become L or something like that? What's L is 10, so let's make D2 go to that. Change that value, and then you can just do, well, you can't really see it up here because it's up at the top, but it's a Mac, but you can go through and you can tell it to evaluate the whole notebook under evaluation. And it'll go through and reevaluate everything. Well, it actually reevaluates the picture. That's kind of silly. And there you can see how the stress changes, okay? So it's pretty powerful. The nice thing also about it is if you do make an equation error, let's say we went through and we made an error the way we did parallel axis theorem, all you really need to do is just change this one equation and then go through and mathematical and just go through and recalculate everything, all right? I'll post this one on Blackboard as well, okay?